Welcome back to the next session of Gyan for today. So, this session is actually focused on machine learning for advanced data interpretation and forecasting in wearable health technologies. So, when you are actually making devices for continuous monitoring, wearable devices, then you need to have some sort of an algorithm or some sort of a processing system which cleans the data automatically for you. And let us say you are monitoring certain biomarkers, then this model or this algorithm should also give you the right value of the biomarker. Let us say if you are monitoring glucose, then it should give you the correct value of the glucose. So, there are many different challenges when if you are using wearable compared to if you are doing POC, point of care diagnostics, or whether you are doing continuous monitoring. So, there are many more challenges in continuous monitoring, because when a person is wearing a device and they are sitting, sleeping, going on with their daily activity. So, these activity actually adds noise to the sensor signal. So, how do you remove this noise from the sensor signal, isolate the sensor signal that you are interested in? Let us say if we are monitoring glucose, how do we identify the changes in signal which are specific only to glucose and not identify, let us say, those related to movement or any other interferences. So, these are few topics that we are going to cover in today's talk right now. So, we will actually split the talk into two parts. The first part is data interpretation, or you can say data pre-processing. So, we want to automate the process of pre-processing. So, we will look at what are the system requirements, what are the specifications for data pre-processing that is required and how we can do that. And then we will look at forecasting. How can you actually forecast analyte levels in advance, and we will take the case study of glucose forecasting as an example and try to understand from there. So, I just wanted to show you why we need data pre-processing. So, this is some data that we collected during an in vivo experiment from an animal. So, on the y axis you have the voltage signal, and then x axis is actually time. Okay. So, this the input voltage actually was representing pH. So, we were actually measuring pH inside the vagus nerve in response to some injections that was given to hormone injections, CCK injections that were CCK stands for cholecystokinin. It is a gut hormone given to the animal. Okay. So, if you look at this signal, we can identify some small bumps here, and these bumps correlate nicely with the injections that we are giving. Okay. So, this is something which is done post recording, like once we have done the experiment and we look at it visually, we are able to identify. So, if you look at this data, you see there is a linear drift to it. Okay. So, it is actually there is a linear drift to it. So, now if we are monitoring pH, and if you can recall from yesterday's lectures, what is the sensing modality that we use for monitoring pH? Potentiometry, right? Potentiometry. So, in potentiometry we are measuring the OCP, open circuit potential, and this OCP has a linear drift to it. Okay. So, now if you can think, if you are making a wearable pH sensor, let us say, or an implantable pH sensor which is inside the body, you will get this kind of a signal and you will have some drift here. So, you cannot directly interpret the pH just looking at the voltage signal. You have to actually remove the drift, and then you can do some sort of interpretation. So, so this is one data from one experiment, let us say experiment 1, and this is the data from another experiment, experiment 2. So, in experiment 2, these bumps in relation to the injection are much smaller and they are not visible. Okay. So, this tells us that okay, we have to have some sort of a processing method that can actually remove this drift, clean up the signal, and so that the device can automatically and correctly estimate the analyte level. Let us say in this case pH. So, this is after cleaning. So, if you look at the yellow plots here, this is after the drift has been removed. So, you can see the peaks nicely, and here as well you can see the peaks nicely. And what is interesting here is you can see some sort of a dose response. You see the amplitude of the peak is slightly increasing as we go from injection to injection. This is because we were giving increasing dosage of the hormone. So, there is some sort of a dose response to it. So, this is this dose response, I mean, even though some bumps were visible here, but this dose response feature was not visible unless you remove the drift from it. Okay. So, this kind of so that is why we need to actually do some data pre-processing before we can do any analysis or any interpretation as to the concentration or pH of the data that we are collecting. Okay. So, this particular data was collected when the animal was anesthetized and the environment was more or less stable, but if let us say imagine if the animal is having the device inside and the animal is moving, it would have been very challenging. Okay. So, there the processing will be much more difficult. So, starting if you think of one of the challenges, that is the first feature that is present in wearable sensors like we see here is actually drift, sensor drift. Okay. So, there is always some sort of a sensor drift. So, this sensor drift can be linear or it can be non-linear. Okay. So, what we see here are examples of mostly linear sensor drift. Now, there can be other interference. So, this is mostly linear. When we talk about non-linear, so this sensor drift, the trend, if we look at this trend here, mostly it is going down, right? It is going down, but it can also change the direction. What will you do? So, you cannot apply a linear fit to it. So, you have to actually do something in real time, so that you are actually able to distinguish between drift and signal. Okay. So, let us say if this in addition to this bump, for example, here it suddenly goes up, this is non-specific, it is not due to injection, and so it is something non-specific, or it could be an artifact that we got while we are actually cleaning the signal. But you can see that there are two ways in which drift can go. It can be linear unidirectional, or it can be non-linear, and of course, it can go in either direction, it can be positive, negative. So, how do we deal with that? So, this is the first problem that we encounter when we develop sensors, wearable sensors. So, generally if you look at, if you can recall the system diagram that we had previously. So, there was an amplifier, it can be a trans impedance amplifier, or it can be a simple OTA, operational transconductance amplifier, that will amplify the signal. Then the second one is the filter, some basic filtering is required to remove the noise, and then this drift is a very low frequency drift or low frequency signal. So, it actually escapes, sometimes it escapes the filter, it passes through and comes out through the ADC. So, in that case actually we have to apply some processing techniques to remove this drift. So, I will show you one of the processing techniques, there are many that are there. So, of course, the features are enhanced after pre-processing, so primarily drift removal. So, we are not there in AI yet. So, we are still in the signal processing domain. Okay. So, this is the example of like from where the data was collected. So, there was the vagus nerve from which we were collecting the data. So, these were actually very small micro spike, that we saw yesterday, pH electrodes. Okay. So, these were micro spike pH electrodes that were inserted into the nerve. The nerve is barely visible because it is this is a vagus nerve from a male Wistar rat, and the thickness of this vagus nerve is around 100 to 200 micron. Okay. So, it is very thin, like a human hair, if I were to give an analogy, and then inserting a spike through that is very challenging, and then again getting the data out of it is another challenge. So, this data which I had shown you earlier is actually taken from this experiment where the rat was anesthetized, the stomach was opened, and the subdiaphragmatic vagus nerve was picked out, and the spikes were inserted, and pH was monitored, and we wanted to see if there is any correlation. So, this hormone cholecystokinin CCK is supposed to elicit some neural responses in the vagus nerve. So, we all know that there are some electrical neural responses, whether this electrical neural response leads to some sort of a pH response or not, that was the experiment that was being done. Okay. So, you can see in this kind of scenario, this is, I mean, the future thought process was that you can make a implantable device inside the body, and you can avoid the problems that you encounter with electrical signaling like noise and interference and all this. So, but because pH is a very slow signal and you can easily filter it out. Generally, when you are recording inside the body, let us say you are recording biosignals inside the body, whether it is neural signals, or you can, if you are recording from a certain muscle, what happens is the EMG and the neural activity, they share the same bandwidth. So, you cannot actually use filters to remove, you cannot isolate EMG or non-specific activity from the neural activity. So, then pH is something which is very, very low frequency and out of the frequency range of the EMG signal. So, you can easily isolate it. So, that was one of the reasons why we were looking at pH. Anyway, so what we observed here was drift and how to remove drift. So, that the next question is how to remove the drift, and this was actually published, this work was published. So, drift can be caused due to various reasons. Just have a look at, so we are familiar with this iridium oxide sensors, because we will also see in the hands on demo session, and these are pH sensors, and we also saw it yesterday. So, they actually have a problem of drift, and drift can be caused due to various reasons: change in open circuit potential. It can be due to background activity, some other activity is affecting the pH, or some sort of a movement, noise, anything. It can be, so if you have a amplifier, if you are using an amplifier with a input bias current in the range of picoamps also, that can also lead to drift. Okay. So, I told you yesterday that we should go for something which is in the range of femtoamps, very small input bias current. So, generally OCP drift is unidirectional, but it can also be bidirectional depending upon if you are combining multiple causes of the OCP together, then it can be bidirectional also. And this is, so these are some typical recordings that we collected. So, it's very hard to see the peaks here. You can see somewhat of a peak here. These are visible, these are the injection peaks, but you can see with the with the drift, it is very hard to make any interpretation out of it. Okay. Only if a person can manually look at it, remove the drift, and do it post recording, then only you can actually see. So, we try to develop a method where you can do it in real time. Okay. So, how we can do it in real time, we are going to see. So, generally when we are collecting signals, the signal here, so we are actually, if you are observing signals in the computer, so we are actually converting analog signals into digital signals. So, this pH is also an analog signal, and this analog signal generally when we do the sampling, we do at a very high rate of sampling, that is 10 kilohertz, 20 kilohertz, depending upon the bandwidth of the signal. There is something called as Nyquist frequency. So, Nyquist frequency is Nyquist criteria, that your sampling frequency should be at least twice the signal frequency. So, generally we want to satisfy the Nyquist frequency, and we sample at a very high rate. So, what we have to do is, now for a pH, actually it is moving very slowly, the signal is changing very slowly. So, bandwidth tells us, actually just to give you a background, how fast a signal is changing with respect to time. So, if a signal is changing very fast, then we say that it is a, with respect to time, then we say that it is a very high frequency signal. If the signal is slowly changing, then we call it as a low frequency signal. For example, all these power supply, AC power supply, they are 50 hertz. So, that means the signal is changing 50 times in 1 second. Okay. So, that is what we are indicating. So, pH is a very low frequency signal. Similarly, glucose also, I will come to glucose reading. We generally take a sample every 5 minutes. Generally, all the CGM sensors, they take a reading every 5 minutes, but internally they are sampling at a higher rate, because the electronics is designed for higher sampling rates. And this is the pH signal. You can look at the voltages, different voltages here. So, this is the kind of peak that we want to detect. So, this is in relation to, this is the change in pH that happens due to an injection, and that we want to actually detect. So, this actually is inverted, because the previous one is actually, if we go back to the previous slide. So, this is a voltage in voltage signal, and the sensitivity is generally, as we saw yesterday, it is minus 0.075 millivolt per pH. Okay. So, when you convert it into pH, so the signal is inverted. Okay. So that's why we have. So if the voltage is increasing, that means the pH is going down. So that's why. So this signal generally, this what we are showing here is after drift removal, and so it's easy to look at the dose response. So this is the dose response curve. So with respect to different dosage of CCK, 50, 100, 300, 1000 picomoles per kg, you can see that there are different responses or changes in pH. Now this is done post experiment. Okay, so how do you do it in real time? That is the bigger question, because you want to have a device which will do it in real time. So this is one approach in which we have actually used previously. So we used actually a CIC filter. So the CIC filter actually reduces the sampling rate from 20 kilohertz to around 5 hertz. You can actually program. So this CIC is called as a cascaded integrator COM filter. They are generally used for reducing the sampling rate from a very high sample rate to lower sampling rate without sacrificing the signal quality. So CIC filter is doing that. And then we have an algorithm, a method for drift reduction. So you first detect the drift and then you subtract it. So I will show you how it is done. It's very simple. So this is the CIC filter structure. I am not going into detail of that, but if you look at the this is the you can say the mathematical approach to remove the drift. So you look at the present sample, subtract it from the past output, and then you can generate the present input with the combination of the past and the present output. Okay. So this simple mathematical formula, it can help you remove drift in real time. Okay. So if you are, it can be applied to any other biosensors also. You can apply it to this method. So this is called as a correction factor. So this CF factor controls what is the contribution of this term to the overall mathematical expression. Okay. So by controlling this CF, you can actually control how much drift you want to remove. So you can do some sort of a correction on that. So that is one approach. That this is a pre-processing method. No AI involved here. It's simply the mathematical model that can be used to do it. And here, so it works quite well. Yes. So it works quite well, but the problem arises when we have lot of non-specific changes. So in the previous signal, we did not have many non-specific activity, mostly linear in one direction or the other direction. But let's say you have lot of spikes, you have so it's very hard to actually distinguish between these. So that is where we will be using AI. So if you have, so generally you have this kind of activity, right? We have a linear, very slow changing drift, and then we have some changes in the pH. So the slope of, so this, if let's say this is specific to injection, this is changing at a faster rate compared to this. Okay. So this method is applicable there. But if let's say this drift is also changing at the same rate as the pH, then it will be difficult to remove. Okay. So we will look at a much more advanced method where if your signal, if your background signal or the interfering signal is changing at the same rate as the signal that you are interested in, what method to use. So you cannot use this method. So this method is only applicable for non-linear drift removal if the rate of change of the non-specific signal is different or lower than the rate of change of the signal in interest. Okay. So this will be actually coming to the next step here. So we use this method to successfully clean it. So now I will show you some methods which are AI based method, and you can actually use it to do outlier detection. So you can actually use it, let's say you have a scenario where your background is also changing at the same rate as the signal that you are interested in. You can still do outlier detection. You can still isolate them. Okay. So how to isolate that? This is the method which I am going to show now. So this was actually published in a journal paper, and they actually made a chip out of it, like a ASIC, application specific integrated circuit, which I was talking about yesterday. So let's see how they are doing it. Okay. So the way they are doing it is they are actually using a method called PCR. So PCR stands for principal component regression. Okay. Principal component regression. So, this PCR is a method that is used in there is a field of study called chemometrics. So, there actually in chemometrics PCR is used quite frequently to estimate the concentration of an analyte from a signal. Okay. So, here in this particular paper they are actually trying to measure dopamine in the brain with respect to stimulation. Okay. So, if you stimulate certain areas of the brain and there will be some dopamine release. Now, the dopamine sensor actually that they are using, it shows it shows responses due to dopamine. So, this CDA is the response due to dopamine. It also shows changes due to background. It can also show changes if let us say there is a change in pH in and around the brain or in the environment. So, what they did was actually they used this PCR to isolate and also estimate the concentration of dopamine from the combined signal. So, in the combined signal you will have changes due to background, you may have changes due to pH, may or may not, but they have considered it and then you may have changes due to dopamine. But using PCR you can isolate this dopamine change and you can actually calculate the concentration of the dopamine. So, the way they are doing it is, so if you look at this, they have a calibration step where they are manually they are having the sensor, they have a fluid channel and they are actually putting the sensor in the fluid channel and they are manually changing each analyte separately, okay, and they are generating data sets for background. So, the non-specific background signal, they are generating data sets with respect to dopamine, controlled concentrations of dopamine, and they are also doing by changing the pH. In this way they generate a data set and this is their training set actually. This is actually they are actually using a method called as PCA. PCA is an you can say unsupervised approach where you are actually there is not a training step as such involved, but I will explain what it is. So, these are the different data sets that they are getting for only dopamine, only pH and only background, and then they are making this data set A and then they are applying this SVD. SVD stands for single value decomposition, okay, single value decomposition. So, using this single value decomposition they are actually able to generate this matrix. There are 3 different matrices that is being generated. So, out of these one of these matrices is called as the PCs, principal components. Okay. So, these principal components using this principal component you can actually generate a projection of, if you have a signal which is coming in mixed with background and you generate a projection only for dopamine, then you can see how similar this only dopamine projection is with respect to the mixed signal. So, then you can find out what is the contribution of the dopamine only in the mixed signal. Okay. So, that is the approach that they are using. So, using this principal component analysis they are actually able to isolate the contribution of only dopamine, only background, only pH, and then when they have a real time signal coming in, in real time when they are monitoring the brain, they try to match it with the projections for dopamine only, and then from the mixed signal and by finding out the kind of similarity between the mixed signal and the dopamine only projection, they are able to isolate what is the dopamine contribution to the signal. So, they do one more step ahead. The first step is PCA. Okay. So, this PCR actually is a combination of two machine learning methods. The first one is PCA, then the second one is linear regression. Okay. So, this PCA will help you isolate the signal which is specific to dopamine, and then using linear regression you can actually estimate the concentration. Okay. So, these are 2 different steps. So, in combined they are also called as PCR, and this PCR actually is used in. So, what they do is when they make the chip actually they cannot do the training on the chip itself. So, what they do is they do the training of the chip and then they generate this principal component matrix and the regression matrices that they load into the chip, okay, and then they can use the chip for concentration. So, we also used a similar approach in this similar way. So, let us say so this is, you can see here. So, the yellow one is the actual data, and then the projected data. Let us say I am only interested in the CCK data. So, you can see that the CCK specific signal, if there is any component in the waveform real time data which is matching with the CCK response, then they are overlapping nicely, and the residuals is very low. Residuals means the difference between the two is very low, and when they are not matching, you can see that there is a difference, and by using a threshold on the residuals, you can kind of understand whether the change is due to CCK or not due to CCK, even though if it is linear. So, this approach is a way to do non-specific drift removal, or you can do outlier removal using some sort of a machine learning method. Okay. So, this is where, so like this, there are actually many different 2-3 methods are there. Actually, you can use non-linear drift for non-linear drift removal, but all these things are done before. So, this is done separate from the actual application. Let us say I am going to use it for artificial pancreas. If there is some noise in the sensor, this is the noise removal part or the pre-processing part that is there. Okay. Now, once I have done it, once I have done the noise removal and pre-processing, now I have to focus on the actual application, which is the glucose forecasting. So, just to I have included these slides just to recap few things. So, we are done with the interpretation part, data interpretation part. Now, we are moving on to the forecasting part, and then in the forecasting we will see how we do the forecasting. First of all, why we do the forecasting, second is how we do the forecasting, and what are the challenges in forecasting. That is what we are going to look at right now. So, as you know, we have been discussing over the past few days, the CGM sensors are mostly monitoring from the ISF, and there is a delay, physiological delay between the ISF and the blood glucose level. So, you need to forecast in advance, so that you can actually stay ahead with the change in glucose levels, and you can do the insulin dosing correctly. Okay. So, the AI model actually sits here in the controller, and this controller actually does two things. First, it does the forecasting. Okay. After it does the forecasting, it estimates the insulin dose, and this insulin dose is given to the actuator. So, this actuator, the insulin pump, is the actuator. Okay. So, in today's session we will only be focusing on forecasting. And these things we have already seen. This is the technology stack that we have. So, yesterday we looked at technology stack 1 and 2. So, today we are looking primarily at technology stack 3. So, we are mostly looking at technology stack 3. Okay. That is the focus of today's lecture, right. So, what is involved in this glucose forecasting? So, essentially you have the patient or the person who wants the glucose forecast. So, you have actually many different factors which are affecting your glucose level. First is the physical activity. So, the major part is actually meal and insulin. If they are taking insulin, then these are the two major contributors to change in glucose level. The other one is physical activity. So, then physical activity also, there are two types of physical activity. There is aerobic, and then there is anaerobic. Okay. So, aerobic and anaerobic will actually affect the glucose in different ways. So, aerobic will lead to decrease in glucose level, anaerobic may lead to increase in glucose level. Okay. So, and this data, this glucose data is collected through CGM sensors, and then we use there is a physiological delay between the blood glucose level and the CGM level. So, we need to do the glucose forecasting, so that we can know in advance what is the glucose level is going to be, and then accordingly based on the forecast you can actually give the dosage, right. So, there are two important factors that you need to remember when you are doing forecasting. First of all, your forecast has to be accurate or precise, you can say. Why? Because you are doing the insulin dosing based on this forecast. Okay. So, if you get the forecast wrong, then the insulin dose will naturally be wrong. Okay. So, that is why they have to have high fidelity. The second thing is the second aspect that we need to remember, the second challenge that we need to tackle is time lag. So, whenever you are using AI models, deep learning models, so there is because they have lot of parameters, so there might be a lag between when you want the forecast, there might be some delay due to mathematical computations. So you want to have the time lag as low as possible. Okay, so this is one, and this is two, and the third one, which is more of a important and desired feature, especially for doctors, is actually explainability. So if you have worked previously with neural networks, you will know that the neural networks are like a black box. So once they are trained, you don't exactly know why they are forecasting a certain value. Okay, so it will be good to have a network which is actually explainable, which is giving some interpretation to the doctor. Let's say that okay, this is happening because of this reason, the forecast has been given due to this reason. Okay, so this explainability is another factor. So there are three factors that we are going to look at. First is accuracy, then time lag, and then explainability. Now there is also another factor which is coming inside this time lag. Let's say you want to have a model which you can deploy it on a mobile phone. Now if you want to deploy a model on a mobile phone, that means the number of parameters required for computation for that model must be very less, so that you can fit in the memory of the mobile phone. That means naturally the time lag will be less. So the more number of parameters you have, more processing, more time lag. But when you are having this lower number of parameters, you will have to sacrifice for accuracy. So in engineering always there is trade-offs. So you have to make a decision which how to balance these trade-offs. Okay, so there is a need for accuracy, but if you go for very high accuracy, you might have very large number of parameters. Then large number of parameters means large time lag. So you have to find a sweet spot where you can balance all these things. Okay, so let's have a look. So the first framework that we used is a very simple framework. I will go into the details of the framework little bit in very shortly. So overall, you have this system here where your CGM sensor is collecting some data, sending it to an app. Then this app goes to a cloud, and then the deep learning model is running in the cloud. For the framework 1, it is running in the cloud, and then it is sending the forecast back to the mobile phone. Okay, for this particular. So basically the training is done in the cloud generally, because cloud has very large number of resources and you can use it. Then the trained model can be downloaded into the mobile app, and then you keep on using it. Okay, and then of course based on the forecast you can give some insulin dosing, and when you are actually estimating the glucose, when you are calculating the glucose forecast, you need to consider multiple parameters, at least 4 parameters you need to consider: past CGM values, insulin dosage past, if you have taken any past insulin dosage, what is the meal, and what is the physical activity level. So these are 4 parameters that you need to keep in mind. So there are many data sets actually nowadays. Type 1 diabetes data sets are lot of data sets are available. Ohio T1D is a very popular data set. It has been there for a very long time. It doesn't have massive number of people, as you can see here, around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they have actually 2 sets, one into 2018 and the other one is 2020. So they have 2 sets. This is the 2018 set and this is the 2020 set, and in total you might have up to maximum around 20 to 30 people in the data set, and they have data for approximately 2 weeks, and they have physical activity data as well. So generally whoever works in this glucose forecasting, they use this Ohio T1DM data set to train their data and actually do the forecasting and test it, and many papers actually use it. Nowadays there are many other data sets have come up. There is one group in Shanghai which has generated a very large number of data, large data set. There is also another website, there is another data set called T1 DXI or DX1 or something like this, T1 DXC I think. So T1 DXC is also a very large data set which has CGM values, meal information, CHO, carbohydrate, that is meal information, and as well as physical activity. And this is available through a website, the website name is Wearable. So Wearable has a good repository of clinical trials, data from clinical trials. It's like a Google for clinical trial data, and you can actually access it by signing different data usage agreements that you are going to use this data for ethical purposes, not for commercial applications and all these things. So this is how the data looks like. As if you look at it, I think yesterday Sanjeev was also showing very noisy data, and then you have some points where the data is missing, This is, we have chosen a good one to show you here, but there are points where data is also missing, and you have to somehow incorporate everything together. So, we also collected some data. So, for validation we train on the T1D data set, and you can actually test on your own data set as well. And this is how, so we collected using the Freestyle Libre sensor that is available in India, and then we did some trial in the hospital. We have our own app and cloud system to collect the data. So, this is a CGM sensor which is implanted on the arm of a volunteer, and generally we put this patch on it. So, this is like a waterproof patch that like if somebody is taking a bath, so you can actually it will not damage the sensor. So, what happens here is, in India the Abbott Freestyle Libre sensor that we have, so there are actually two modules here. This is the CGM sensor, and this is another module called as the BlueCon module. Okay, BlueCon. So, generally the Abbott sensor that we have in India, and they only do NFC readings, near field communication. So, you can only scan when you want. We do not have the Bluetooth version yet. It is supposed to be released in August or September, but we do not have the Bluetooth version yet. So, but we want, ideally we want Bluetooth data, we do not want the user to scan again and again and again. So, that is why this BlueCon module actually sits on top of the CGM sensor. It converts NFC to Bluetooth, and you can get the Bluetooth data in your mobile phone. Okay. So, in this way actually we collected the data, and so this is the network that we have here. For some reason this is from a different presentation. So, this is the data that we have here. So, we have this is the neural network that we initially designed. So, in this neural network actually you see what we use the typical neural networks that are used for time series processing or forecasting, that is LSTM and GRU, but we did some changes to this network. So, we observed that if we use a wide deep approach, so where you have wide deep means all the inputs do not go through all the layers, you treat each input differently, because we observed that CGM data requires more processing compared to insulin and physical activity. Then you pass it through so the number of layers that CGM is passing through is more compared to that of insulin and physical activity and CHO. So, and we used a combination of GRU and LSTM, and that actually led to better performance compared to only LSTM or only GRU. So, what are the metrics? How will you validate your model? So, these are the typical metrics that are there for machine learning models. So, these are forecasting. So, they are like regression metrics that you can use, root mean squared error or mean absolute error. But in addition, because we are working in CGM, we also use this MARD. So, MARD is mean absolute relative difference. So, this is what we have also seen earlier that is being used. This MARD is also used for if you are developing your own sensor, you can compare it with a blood glucose and you can get an MARD value. So, we use the same MARD also to validate the forecasting accuracy as well. So, how good is the forecasting compared to the blood glucose level. So, you can actually use, so you get some MARD value also. So, this generally the units for this is milligram per deciliter, this is in percentage. Okay. So, when we say that the MARD is 6 or 8, it is actually a percent. Okay. So, the difference is only 6% or 8%. So, I guess I do not remember exactly, but the requirement is that it should be less than 10% from regulatory agencies. But MARD is this is one of the parameters. We also use the Clark grid error that we have seen earlier. So, you can see here zone A. So, if you are, so this is the reference blood glucose level, and here you can have the measured glucose level, or in other words you can have the forecasted glucose level. We can have the forecasted glucose level, and ideally you want all the points to lie in region A. Okay. So, region A is where clinically accurate predictions are there. So, there is no major risk to the patient. So, this is called as the Clark error grid that we have seen earlier, and then we have the Bland-Altman plots also, and we have the violin plots also. We have mostly you can actually look at the Clark grid error, and then zone B is also good enough, not bad, not the best, but still workable. And zone C and D are the danger areas which may lead to improper decision making or clinical decisions. So, ideally if you are developing a forecasting method, you want your forecasted points to lie in region A, mostly, and some in region B maybe. So, let us see how our model is performing. So, this is how the forecasting works. So, if you look at the real value and the predicted value, they are matching quite well. In previous works, people who have developed a model previously, so they have a problem at the peaks. Sometimes they will work well, the model works well if the data is changing slowly, but if it is changing rapidly, like in the peaks, whether it is up or down, there might be a difference that we managed to solve here using this model. Second, as you can observe here, there is a delay. So, you can see that this plot, the black plot is leading with respect to the purple plot, and that is because of the delay in processing or generating the forecast. So, there is around one sample delay. One sample is again is equal to 5 minutes. So, this CGM is actually sampling at every 5 minutes. So, there is a one sample delay between the actual and the predicted value. So, not much, but still we would like to reduce it. So, we have used different forecasting horizons. So, you can forecast 15 minutes in advance, 30 minutes in advance, or 60 minutes in advance, but as you increase the forecasting horizon, you are generating more number of points, naturally your computation increases and naturally your delay also increases. Okay. So, this is kind of performance for this is a for RMSE, MA and MARD values for all of these different T1D subjects and all that. This is the Clark grid error. So, if you can look at this Clark grid error, you see some of the points are there in C also, C and D, but majorly most of it are actually in A, region A, and as you increase the forecasting horizon, naturally you get more number of points outside. So, there is some risk, but of course, there is a limit up to how much points you can actually tolerate here. So, ideally if you have 90% of points within the A and B region, then you are actually okay, 90 to 95%. Now, this is another approach that we tried. So, it is always better to update the model frequently. So, if you use an approach which is train once, then the MARD actually becomes poor as you move on with different data sets. But if you train frequently on the same individual, if you are training frequently, you are updating your model, then it is actually MARD is actually improving. Okay. And this MARD is very good. This is the ideal MARD, not the actual MARD, because this MARD is from the forecasted data, not actually not the real not the sensor. The sensor MARD is around 8, 6 to 8. 6 is very good, but generally it is around 8 so that is different MARD. So, this is the forecasted MARD, not the sensor MARD. Of course, this is comparison with the previous work. We are fine with the metrics that we have actually we are actually if you look at the metrics, then we are performing better than the others. The place where we are falling behind is the time lag. So, this is 5 minutes, 1 sample delay, 4 sample delay, and the delay increases as you go for larger number of forecasting window. Okay. So, now essentially now we want to actually, there are two problems that we want to resolve. Somehow we are performing well in MARD and the other performance like RMSE, root mean squared error and other metrics there, but ideally we want to have low delay as well as we want to add some explainability to the model, so or interpretability to the model. So, for this actually we tried a new type of network which is called as the neural basis expansion network, and the neural basis expansion networks, they are actually interpretable. So, they give you a trend component and a seasonality component. So, they tell you exactly why a certain forecast is given and why the forecast is there, but the accuracy is not as great as the previous model. So, we tried to enhance this by using multi-head attention layer, which is within the. So, this is the typical block of a neural basis expansion network. Generally, neural basis expansion, they work with only one input. So, you can actually expand it like we have done it by trying to, we modified the neural basis expansion network to use multiple inputs. So, at least 4 are there: past CGM, past CHO, CHO is for meal, past insulin data and past physical activity, and then you actually try to have these are the different. So, we generally in neural basis expansion network, we enhance it by using this multi-head attention layer. Okay. So, this multi-head attention layer helps in improving the accuracy quite a lot, the MARD quite a lot, the RMSE quite a lot, but it actually reduces your interpretability to some extent. Okay. So, we call this as a partially interpretable model. Partially interpretable, we get some idea of why a certain forecast is given. I will show you in subsequent slides, but at the same time because this is a bit of a black box, so it is not completely interpretable as a standalone neural basis expansion network. So, in that way actually we try to improve the accuracy as well as so this work is already published, and in the interest of time, as we are moving a little bit fast, so you can actually look at the MARD. Let us go to the comparison where, so yeah, so nice, you can see here the delay is not there. So, in the previous one there was a 5 minutes delay, the delay has disappeared here, they are actually almost overlapping. So, in 15 minutes, and in 30 minutes there is a small delay, and in 60 minutes there is actually a delay of only one sample, around 5 minutes if I remember correctly. So, the delay is much better than the previous networks, but and at the same time there is also some level of interpretability. So, let us see whether there is any improvement in the forecasting accuracy. So, if you look at this plot here, then this gives us in some idea that there were less number of points in the C region compared to the previous network which I had shown you, and there is more number of points in the A and B or the safe regions. So, A and B are the safe regions, right. So, if you look at the comparison also, we get much less time delay as well. So, previously if you remember it was around 40 and we brought it down to 15 point something. So, the time delay has improved, and at the same time the MARD value also is lesser compared to the previous work. So, the best was 15.27, now it is 12.15, and this way we have actually improved the MARD as well. So, there are many advantages of this network. The first advantage is time lag is less, second is accuracy is better, it has high fidelity forecasting, third is there is some level of interpretability also. So, this is how actually interpretability looks like. So, let us say this is the overall prediction. So, the overall prediction is the blue window, that the blue plot that we are getting. So, this is the overall forecast. Now, you can interpret why this forecast has been achieved, because this forecast is a combination of the seasonality component and the trend component, okay, seasonality and trend component. So, this when you combine these two components, you are getting this kind of data. So, you can say the trend component is much more of a short term change, it captures short term changes, and seasonality is capturing long term changes. So, it is actually coming from stock markets where you have this trend and seasonality ideas, where you look at short term changes as well as long term changes. So, it is telling us that okay, the glucose level is increasing here because my based on the seasonality component, there is an increase in the seasonality component that is causing the glucose forecast to increase. Okay. So, in this way you get some idea, and seasonality is of course the long term component, and you can say that okay, because the long term, so the patient has seen around this time, mostly the patient has seen an increase in the data, that is why it is actually giving you larger forecast compared to the trend. So, there is a combination. So, it is you are able to break this component into two parts, the trend and seasonality. Now, there is these are some mathematical equations which are actually showing us how the overall model works nicely. So, you cannot just fit the multi-head attention layer into the neural basis expansion. You have to do some there are some corrections and some factors to keep in mind, but we are not going into much detail of these factors right now in interest of time, because I want to show you some other interesting application. So, these equations also enable us to extract the trend and seasonality visualization of a glucose forecast. So, why a certain forecast has been given, and what is the contribution of the trend component, and what is the contribution of the seasonality component. So, in this way you have some level of interpretability, and this interpretability actually helps keeps the doctor happy as well. They know exactly what is working in what way. So, you can also look at different layers. So, when you are actually so there is a parameter called as flops per G. So, this flops per G is a metric that we use to understand how fast computation is done, what is the requirement of the computational requirements of a particular model. Okay. So, this model actually has lower flops per G compared to some of the previous models. It is not the best, but still it has comparatively less compared to, let us say, RNN, dilated RNN. So, this DRN stands for dilated RNN, but still we can actually improve somewhat in this region. So, it is better than TCN also, this another network. So, there is some improvement, also better than deep ensemble network. So, in this way, if let us say you are developing your own model, so the first parameters, think about this, let us say you are developing your own model. So, what are the parameters that you will test or look at? First is the RMSE, MARD, MAE if you like. RMSE, MARD is enough. Then you look at the time lag, then you look at the processing requirements. So, the flops will give you the processing requirements. Now, this flop, if you take any processor, let us say you take your Intel processor, the Intel processor will have certain flops. So, if your flops is lower than the specified flops, then you can deploy this model on the processor. If it is more, then you cannot deploy. Okay. So, there is this kind of simple comparison. So, that is why people look at the flops per G as a metric. They do this analysis to understand where they can deploy their model, whether they are able to deploy it or not. Okay. So, still we are not able to deploy this model yet on an edge device. So, we want to reduce the flops further to be able to deploy on the edge device. When I say deploy on the edge device, I mean training as well as operation on the edge device. So, operation can happen in the edge device, but right now we cannot do training. Training requires lots of flops per G. So, that is why we want to actually, generally training is done in the cloud, the trained model is downloaded to the app. So, that is how the AI driven, most of the AI driven apps are being used. Right. These are some publications related to that. Now, coming to the interesting aspect, I had shown you one plot earlier where I showed you that there is a data missing. Okay. So, this happens, this is a CGM data for a particular individual. There is actually a missing data point here. Now, if you have missing data points, you cannot actually do any sort of forecasting. Okay. So, in order to deal with this, we try to use there is something called as generative adversarial networks, GANs. Okay. Generative adversarial networks. So, these networks were actually developed by someone called as Ian Goodman. It was part of his PhD actually. And these generative adversarial networks are very versatile networks. You can generate images, and here we have adapted that. So, you can actually generate human faces. If you go to, if you can Google now also. So, if you type this person does not exist, there is a website. So, this website actually generates unique faces. So, it is not the face that is generated is not the face of a real individual. It has been trained on previous data sets and is generating unique faces, and it is very much similar to a human face. So, this model that we are using, we are adapting it. From an image to a time series based data. Okay. So, we have adapted that to generate the missing data points here, to replace the missing data points. And while doing that, actually the way generative adversarial network works is there is a generator and there is an adversary. So, generator generates different points, it generates a series of points. The adversary actually looks at these points and tries to see whether it matches the probability distribution, the desired probability distribution. Okay. Let us say you want to generate the face, then it has a certain spatial distribution of pixels. So, the adversary actually ensures that it matches the generated points matches the actual. So, it actually removes those points which are noise, and it only keeps those points which are actually matching your desired probability distribution. So, it is all about matching a certain probability distribution. So, here also you can see this is our GAN network, and what we have done also is that there is this discriminator or the adversary. So, this discriminator is we have the generator and then we have the adversary or the discriminator. So, this discriminator actually we observed that if you use LSTM for long sequences, you have a better generation, better discriminator, and if you use GRU for short sequences, you have a better, rather than using a single model for all sorts of sequences. Let us say I want to generate 60-minute data, that is a long sequence, then I would go for an LSTM as a discriminator, and otherwise I would go for GRU as a discriminator. So, this kind of distinction if you use, then you can see it performs quite well. So, here if you look at this plot in the bottom here, so you have the blue plots which is having missing data points, and the green one is actually generating the missing data points. Okay. So, it is actually replacing this real data with synthetic data, and then when you are training your AI model, you can use a combination of real and synthetic data and you can train. Okay. So, models require a lot of data to train. Much more detailed diagram, nothing much to see here, we have already discussed. So, what do we classify as a long sequence and a short sequence? So, generally when we say it is a short sequence, we are using GRU. So, generally we want, if you want 24 maximum 24 points to be replaced, then we call it as a short sequence, we would go for a GRU discriminator. And if we are having very large number of data points that we want to generate, we use for an LSTM discriminator. Okay. So, the way to validate this is, it is not your typical RMSE, root mean squared error, or mean absolute error. We generally use something called as PCA, principal component analysis, and TSNE. So, TSNE is another method, it is a dimensionality reduction method. So, you look at the spatial distribution of points, the actual points and the synthetic points, so they should overlap. So, if they are overlapping in this space, principal component 1 and principal component 2, then it means that you have a good GAN network. If they are not overlapping, visually it can tell you that okay, this GAN network is not good enough to be deployed. Okay. So, here if you look at it, it actually matches quite well, and then you can also generate a quantitative value. So, this is qualitative, you can look at it. You can also generate a qualitative value which we call as a discriminative score. Okay. So, the lower the discriminative score, the better it is for the GAN network. Okay. So, I think this is where we are actually replacing. So, not only you can generate CGM, let us say you have some missing data points. Generally, the insulin and the meal information the user has to manually enter in the app. So, if they forget, so that data point is missing. So, if you know an overall trend, you can replace those missing data points as well, and you can replace that with a very good fidelity, good accuracy actually. And then you can use a combination of these, you can generate both physical activity data, you can also generate lifestyle data, which is the meal information, and this is meal information, and this is the insulin data, and they are actually, you can see get a visual idea of what is the difference between the generated and the actual points for a certain example, for a single subject. So, this is use of generative AI for certain application in diabetes management. Okay. Right. So, there was only one previous work which we were able to compare, and we have slightly better result in terms of discriminative score compared to the previous work in terms of imputing the missing data points. Right. So, right now what we have here is, okay, what we have covered broadly in this topic is, we require some sort of pre-processing in the sensor, especially if you are using wearable sensors. So, we have to account for linear drift, we have to account for nonlinear drift, we also have to account for nonlinear drift which has a similar profile to the target analyte of interest. So, linear and nonlinear drift which are not similar to the peaks that we observe, the rate of change, we can easily remove using a simple mathematical model. If they are similar, then we can use an AI based approach, which is this PCR, principal component regression, or you can use simply, if we just want to do qualitative, then you can simply use PCA as well, do a projection, look at the residuals, and if the residuals are very small, then it belongs, and if it does not, then it is not due to the target analyte. That is the first that we covered. Then we also looked at AI based data forecasting. They perform better compared to other approaches. So, there are other approaches which actually you can estimate the data, you can also use mathematical models, but AI based approach seems to work better. We have also learned that GAN based methods, so generative adversarial network based methods, can be used to replace missing sensor data points as well. So, I would like, when the session is over, so you check out this website, this person does not exist, and you would be surprised what the AI can do. Okay, this person does not exist. So, it actually generates unique faces, and it is very it's hard to differentiate between actual face and the generated face. So, I think that is the end of my slide. If you have any questions, you can ask. Yeah. Sir.
Thanks. Nice presentation. Everything is perfectly fine, very much understandable. Just a quick question. You mentioned about time lags.
Yeah.
Now you're talking about time lags which are more related to your processing time lags.
Yes. Yeah.
How do you account for the physiological time lags?
So, that's why we are forecasting at least 15 minutes in advance. So, that is the way to account for your physiological time lag. So, we have different forecasting horizons. So, if you go back here, yeah, we can see here also. So, here you have these different forecasting horizons. So, you can forecast at least 15 minutes in advance. So, that is the bare minimum physical that is the maximum physiological delay that you have. And then, so generally what you will have is this delay plus the processing, let us say 5 minutes is the processing delay.
But then why have you gone from 15 towards 60? Why haven't you gone from, because I think the range is normally from
very small,
very small,
very
yeah,
small, yeah.
4 to 15.
Yes.
So why have you gone the other way of the spectrum? Why haven't you gone?
So so it actually, it's a way to stress test your model.
Okay.
So if you can do very well for 1 hour, then you will do very well for 15 minutes.
Okay, that
That's
makes
it.
sense. Great. And you also mentioned about those different noise and stuff, drift and stuff like that.
Yeah.
And are you also accounting for any movement artifacts that?
So yeah, so movement artifacts are generally very fast changing.
Yeah.
So let's say if I move my hand,
Yeah.
it's like a peak. So it's like a very fast peak compared to, let's say, so this you can remove using a low pass filter.
Okay.
So that filtering is already there, low pass filter. But if you have, let's say, if in case of neural signals, this is a major problem in case of neural signals. Let's say you have EMG as well as you have neural activity, and they share the similar bandwidth, and then it is hard to remove. You have to use this kind of some other approaches to remove that.
Yeah.
Okay. So in sensor signals, generally, let's say we are taking sensor values, let's say every 5 minutes. So what CGM sensors might be doing is they sample at a very high rate, and then every 5 minutes they are averaging the data and giving you an average value. So when you average out, this peak actually disappears.
Yeah, makes sense.
Yeah.
Okay. The other question I wanted to ask is a very general one.
Yeah.
I remember having this discussion there, and many times we've been asked to be careful about not using chemometrics.
Yes.
And classify that as machine learning stroke AI.
Okay.
Like
Yeah.
even and when I was observing your presentation there,
Yeah.
you mentioned a lot of those existing methods, traditional methods, which are used with electronic sensors, like removing drifts, having those
Yes.
filters and stuff like that.
Yeah. Yeah.
I mean, do you also risk that having that fine line between your traditional methods and people classifying even those things as machine learning and AI tools?
Filters generally they don't consider as AI,
Okay.
but this PCA, principal component analysis, although it has been there for a very long time,
Yeah.
this chemometrics is a very old field.
Yeah.
People nowadays are telling that okay, PCA is part of machine learning.
Yeah.
It's a part of dimensionality reduction. So that's why I mentioned.
So what are your thoughts? Do you think it's part of machine learning, or do you think they should be separated from machine learning?
I think it is a part of machine learning because it is used quite a lot for data analysis applications, sorry, data science, for these applications. I mean, I'm being a little bit partial to the machine learning
I know.
side.
I mean, because I'm having this problem because I come from this traditional field of
Yes.
analytical chemistry,
Yeah.
where people who have been working on chemometrics are very, very, firm that they do not want to.
So they classify this as a statistical approach.
Exactly.
Yeah.
So it's
But
more statistical rather than actually machine learning.
Actually, that is true. That is the fact, because most of the machine learning is a mixture of statistics, probability, and all these things. So yeah, somewhere it falls in
In the gray area.
Gray area.
Thank you so much.
Thank you.
Sir, my question is, you have shown the data for continuous monitoring. What
Yeah.
if we are taking point basis samples? Like for, I have taken one sample at 1 hour, then 6 hours later one sample, like that 24-hour cycles. And if my sensor is targeting 2 analytes or more than 2 analytes, in that case the signal will be very much mixed, right? So let's say I am targeting glucose along with lactate and along with some sodium, potassium, like that. So in that case, how can we like pinpoint that this is the glucose sensing and this is the lactate sensing, like that? It's a mix. It will give us a mixed signal, right?
So whenever you are monitoring different analytes, you use different sensors. So for you cannot have a same sensor that is reading glucose and lactate at the same time.
Now, what if the signal bandwidth is falling in the same region?
Right. So not the signal bandwidth. I would say, let's say you have a glucose sensor, and then glucose sensor also has issues with other interfering agents. Let's say ascorbate or acetaminophen. I'm just trying to rephrase your question and try to understand. So the glucose sensor will give you a signal even though there is no change in glucose, but there is change in, let's say, ascorbate, right?
Yes,
that is your question.
Yes, yes.
So how do you distinguish between two?
Yes, yes.
So if you have trained this chemometric, so it's very hard to do. For chemometry, actually, you require at least a set of data points. It's very hard to do it in spot measurement. So this chemometry actually comes from NMR, right? Actually it originates from these NMR curves. So you require a continuous form of data to do. For spot measurements, it will be hard. One thing you can do is sometimes people use differential measurements. Differential measurement means, for example, you have a sensor which is reading your target analyte plus background, and then you have another sensor which is only reading background. So you can subtract this differential. Yeah, exactly.
Any other questions? So I have one question. So you have worked with some clinicians as well, you were showing.
Yeah.
Right. So how much the clinicians have the confidence in the missed data or the data which you are trying to forecast? What's your experience on that?
So my experience is that so clinicians like to understand why what is happening. Like for example, if you add some level of explainability to your AI model, so some clinicians, at least those who have worked with, they are open to using it. Okay, so it leads to the question is whether it is widely adopted or not. So that still we are actually going through a phase of. So this is now the phase where more and more AI is being used in certain applications. It's a slow process, but it's a process of acceptance. So some people are open, some people are critical.
So
It depends.
why I am saying is that, see, this one is the glucose sensing. So here we have a continuous monitor where few misses might be there,
Yeah.
where you are trying to fill the gap with the AI model and then forecast, which is pretty much robust. In some sensors, it may not be too much. So less of the data, and then you use more of the AI model to do that. So
Yeah.
how the clinicians respond to those things?
So there are also like so it's, I would say that, okay, like for example, if you are there are certain papers and some work, people have actually tried to estimate blood pressure from PPG signal as well. Okay, so the same oximeter that we are using, they try to estimate blood pressure. So some people are acceptable towards that, but they also say that, okay, this is not as good as the cuff monitoring that you have. So it varies. So it also varies on the application. If you want just a qualitative estimate, then okay, it's fine. But if you want a quantitative, very accurate, then you require a good method. So that's.
So Dr. Sanjeev, can you comment on how the clinicians in the UK have the confidence on these type of the models? And
Well, I mean, I would just say it's the same thing what Khalid mentioned. It's well-being versus clinical judgment, right?
Yeah.
And as far as AI is concerned, I mean, I know a lot of oncologists have started using AI picture-based
Images.
decision support systems, wherein they are more happy to use AI for their clinical decision support system. So, in fact, now we use the term clinical decision support system, wherein you are using the AI tools, and they have a lot of confidence in that because they need more support, and this AI is based on machine learning and things like that, the models that clinicians have started understanding. So some of the latest, the new clinicians who have just passed out are now doing a PhD in the area of AI so that they
Yes.
can understand it better
Yes.
and understand the technology better and have more confidence. So
Yeah.
it's all about having confidence in the technology.
Yeah.
And I think with time, more and more clinicians are getting involved in machine learning and AI, and they themselves are getting involved in handling all the records. They're actually going back, digging all the previous records, and trying to make sense of the data. So they try to do what we call as the whole process of stratification is based on AI and machine learning. So there's a big effort in this direction, especially by the clinicians in the UK, and they're having more confidence on this technology.
Yeah. So I also have a collaborator. He works in the US. In his university, actually, they are actually running some courses specifically for clinicians. So clinicians can actually learn about these AI methods, and then they actually it might help in increasing the acceptability of AI in these things.
Any other question, guys?
So I wanted to ask that does it take into account like the relation between two analytes or multiple analytes while there is a missing in data?
Missing data point.
Yeah.
No, the assumption is that that is already dealt with in the sensor itself. Okay, the sensor itself, we are assuming that the reading that we are getting, it's specific to glucose only. So the imputation, the data replacement or synthetic data generation is not considering that. So it's working on the assumption that the sensor is giving me good data.
Okay.
Any other? So I think we can conclude the session.
Thank you.